Welcome to part one, I suppose, of rate law. Here we're going to explore rate law using the ratio method. In the part two video, you can explore the rate law using an algebraic method. And so everyone's going to sort of find the one that works for them. So in this case here, we're just going to be using our mental math kind of strategies, but feel free to grab a calculator as well and be using that, because oftentimes folks do like to use that, especially when they're dealing with decimals. So first step is to find two trials where the values are consistent. So here we have, and I'm just going to really focus only on the first three. So the bottom 4 and 5 we're going to be using in further questions, but there's stuff missing, so we can't really use them now. We see A and we see B. So these are part of our equation. We want to see what effect changes in the concentration have on rate. So that's the whole point of rate law, is, trying to determine, is this a first order, second order, zero order reactant? What is the effect that this substance has on rate? So let's find two trials where one substance stays consistent. So here I see in trial 1 and 2, A is 0.5 and 0.5. So if we ever saw any changes in the rate, it's not because of A, because A is the same. So there's no change in A between the two separate trials. So everything that we see must be because of B. And I like to look from 1 to 2. So I look always from the small number to the big number. So I'm going to look from 1 to 2, and I'm going to say to myself, you know what? I see that, and I know that that is 2 times the amount. If you don't see that, take your big number divided by your small number, and you get the number 2. And so from trial 1 to 2, the amount of B has doubled. So we've doubled our amount of B. And so we want to know what effect it has on rate. So going here, if we did take 2.4 divided by 6, we would see that this is having a 4 times effect on the rate. And so we would ask ourselves, okay, if you doubled the concentration and you saw the rate quadruple, what must the effect be? Is it a 0? 2 to the power of 0 makes 4. 2 to the power of 1 makes 4. 2 to the power of 2 makes 4. So this must be, B must be a second order reactant. So when we look then at A, we want to find two trials when B are consistent or steady, and then we can start looking at A. So I'm going to look here between trial 1 and 3, because those guys are locked in at 0.7, so that's great. So I'm going to go from 1 to 3, and I'm going to say, oh look, we've got a tripling from 0.5 to 1.5. We've got 3 times more A in trial 1 and 3. B stays the same. So what happens to the rate? I tripled the A. What happened to the rate? Nothing. Probably if I put 6 times as much A, I'd probably still have the same rate. So what we would say then is A is a 0 order reactant. So in terms of kind of setting this up, how did we know that? 3 to the power of what makes 1? Because it's 1 times as big. It's the same. So 3 to the power of 0. Now, we're going to write out this rate law. So rate is going to be equal to K, and that K is going to be our constant. It's going to be specific to our reaction. It's going to be specific to temperature. And then we're going to have A. Well, we don't show, because it's a 0 order reactant, we don't show it. So normally we would be like saying, yay, it's a 0 order reactant, and B is a 2nd order, but we don't actually show that. So for our final answer, we would only be showing rate equals K times the concentration of B squared. Now, in order to solve for rate or solve for B, we need to know that value of K. And one of the easiest ways to do that is just to find a trial, where you know all the values, and substitute and solve for K. So that's what I'm going to do now, is I'm going to solve for K. Because we really can't move too far forward without knowing what K is. So let's just take the first trial. And we're going to substitute into the spots. So the rate is 0.6. So I'm substituting in for rate. K, we don't know. That's what we're trying to solve for. B is 0.7. And it's all to the power of 2. So don't drop your exponents or your orders. That's like critical. So we want to just kind of expand that 0.7 times 0.7. So it's not times by 2, it's times it by itself. So we should have 0.49. In order to get K alone on one side, we're just going to divide by 0.49. So instead of times, we divide. Always do the opposite operation. And then we make sure that it's balanced, that it's on both sides. So now we have a value for K, and we can start to substitute in to solve for some of these other values. So let's do that first one. In trial 4, we know the values for A. It doesn't matter, you're 0 order, we don't care about you. We know the values for B, but we don't know rate. So we're going to substitute into our rate law that we created. So the rate is the thing that we're going to, so we're solving for rate. So we're solving for rate. K we know is 1.224. B in trial 4 is 1.8. And we, again, can't forget the squaring. So once you get all that stuff and you get that going into your calculator, you should be able to just hop right out into a final answer for rate. And you know what? It's a great idea to just go back and double check, like, if it's on the right track, because decimals can get tricky, So 3.9, does this make sense? And I would say, if B is 1.4 and you're getting 2, 1.8, yeah, this seems like that's a reasonable amount. If it, let's say your answer was 39, we'd want to take that back a notch. So for our next one, we're going to be solving for the value of B given the rate. So this one is going to require just a few more steps, but let's substitute the rate in for rate on rate law. We'll use our value for K. And then what we're trying to solve for is the b. So we're going to put an x in that spot. And again, we're going to include the square. So to get x alone on one side, we're going to unmultiply here. Do the opposite of multiply, or divide. And we get 1.634. Now, just as a quick reminder, if you want to get a single x, the way you unsquare the number is to take the square root. So the opposite of square is square root, and that actually can cancel the square. So when we take the square root of 1.634, that gives us just one single x here and a value of 1.28. And that is the moles per liter of B that we just found. So again, it's a good idea to double check to make sure, did that make sense? 1.28. And I think in the context, 2.4, 1.42, I think 1.28 is about right. So that was sort of the full picture. I'd like to just look at one more because I think the challenge to rate law is this part, setting it up. So in terms of the ratio method here, I just wanted to look at one more sample and talk through how to get the initial rate law itself. So starting with our fresh sample, we're looking for two trials where one of the particles are steady or consistent. So I'm immediately drawing, my eyes are drawing here because I see the 0.25 and the 0.25. So I want to play between these guys. So I'm going to just, it's not always like, it's just, I use the smaller number going up and into the bigger number so that I can say 0.22 goes into 0.66 3 times. And again, if you want to take the big number divided by the small number, you can get 3. But then that we also have to look in the same direction over on the rate and say, so if, so this is for D. If my concentration goes up by 3 times, what happens to my rate? And here my rate goes up by 3 times as well. So the question is what power is this? Is this a 0, 1, or a 2? And when you have anything to the power of 0, your answer is actually 1. So this is an example of 3 to the power of 1 is equal to 3. Therefore, D must be a first order reactant. So looking at trial 1 and 3, we can see in trial 1 and 3, D stays the same. And now I'm going to look here from 3 up to 1. So here we were looking down, this way we're looking up, but I'm picking, this direction to look because I want the little guy going into the big guy. And again, I'm getting that 3 times growth. Between trial 3 and trial 1, there was 3 times as much C. What happened to the rate? Oh, wow. We're going to have to look at this on our calculator. So if you did 13.5, sorry. So 13.5 divided by 1.5. Maybe you knew that already. It's 9. So for C, we had 3 times the concentration, but we saw 9 times the rate. So what power helps 3 become 9. If it's 3 to the power of 1, it will be 3. If it's 3 to the power 3 of 2, that means you take the base times itself. So 3 times 3, yes, makes 9. So the concern is that some people would use a 3 here, and actually 3 to the power of 3 would be 3 times 3 times 3, or 27. So this is a 2, which makes a second order. And so in terms of writing out the rate law for this, you would write, and you have to write out this full rate equals K, and then you would have C to the power of 2, because it's a second order reactant, and D to the power of 1, which we can just leave as that. We don't normally write the little 1 there, but that's showing that that's a first order reactant.